Welcome. In this video, we are going to discuss about F distribution. Basically, we start with the chi-square random variate. So let chi-square of m denote the chi-square random variable with parameter m. So basically, this chi-square is the sum of squares of m different identically and independent and identically distributed standard normal variates. So what they are trying to say is that the chi-square of m is the summation of m different uh, using m different identical and independent standard normal variates. Okay, so this is what it is. Okay, so it is basically the sum of all these things. And f distribution, okay, f distribution with parameters m and n is defined in the form of that chi-square of m divided by m whole thing upon chi-square of n divided by n. So this is how it looks like. Okay, from this we are very well able to see that f of mn is same as that of 1 upon f of nm. Okay, and here also with the level of significance we will have to read the values from the table that I have shown in these two slides. And when we are about to deal the problems, I will explain you how to read the values from this table. Okay, and moving further, in this we are going to test the inference concerning two variances. So when from this heading itself, it was very clear that we are going to consider two normal populations with two different variances. Okay, from the two different populations, we are going to take random samples from each population, one of size n1 and the other of size n2. So it says that the population, the sample size that we take need not be the same, maybe the same. Okay, but generally it need not be the same. Okay, from the samples that we have taken, we can very well calculate the sample variances. Now the result is that s1 square upon sigma 1 square whole upon s2 square upon sigma 2 square. This is what we define it as f statistic. Okay, this is a f random variables with parameter nu1 and nu2, which is one less than the sample size. Okay, if population variances are equal, that is sigma 1 square is same as that of sigma 2 square, then our f statistic is s1 square upon s2 square. Okay, and this f alpha of nu1 comma nu2 denotes the number such that the area under f curve is right to the, that is here if you see in this figure, if this line is the alpha value, so f alpha of nu1 comma nu2 is the shaded area. So this is what they are trying to say here. Okay, and when we use the statistical table, values are available for alpha equals 0.01 and 0.05, and we will test the equality of two population variances. And this is the assumption that we made, or this should be there for testing t-test concerning two means. Okay, moving further, here the null hypothesis would be sigma 1 square is same as that of sigma 2 square at the level of significance alpha. Okay, and the test statistic f is f can be defined accordingly. If you see, if the alternate hypothesis is sigma square, like if they are not equal, then what would happen? Either of them would be bigger, right? So if sigma 1 square is bigger than sigma 2 square, then accordingly f is defined. Okay, and we will reject h naught whenever the calculated f is bigger than the value of f that we read from the table. Okay, in a similar way, if sigma 1 square is smaller than sigma 2 square, then accordingly it changes. Look at it, s2 square upon s1 square is the test statistic. Okay, but the rejection criteria is same. But and notice that when we denote the parameters, that also changing accordingly, right? If this is not the case, not equal to is the case, then we will have to correspondingly choose the higher sample variance to be in the numerator, and the lower one, smaller one, in the denominator, and corresponding sample size should be used here. Okay, moving further, we have a problem. Given that the following samples taken from two normal populations, test for the equality of variances. Okay, and if you count in the sample 1, we have 8 values, and in the sample 2 as well, we have 8 values, and the level of significance given is 0.02. Okay, we are just asked to test for the equality of variances. So the alternate hypothesis is not specified, so we take the alternate hypothesis as sigma 1 square not equal sigma 2 square at the level of significance 0.02, and n1 and n2 are 8. So we will have to calculate sample variances through the calculator by the formula that we have seen in the beginning of this course, right? So using that, we just calculate s1 and s2, and we can very well define the test statistic, out of which we are able to see that s2 is as the larger quantity, so s2 should be in the numerator. So s2 square upon s1 square is the test statistic. We just calculate the value, and we found out that it is 1.5447. Okay, now we will have to find, so not equal to is the case, right? So we will have to find f alpha upon 2 of nm minus 1 and nm minus 1. Okay, so here 8 and 8, therefore we will have to find 7 comma 7 for the level of significance alpha upon 2, so it is 0.01. Now coming back to the table, 0.01, this is the case, right? So here level of significance for various things are given, and this is 7 and this is also 7, right? So 7 comma 7, that is 6.99 for this 0.01, isn't it? It is 6.99. So that is the noted value. Now you just compare these two values. The calculated value of f is smaller. So in what case we can reject? If the calculated value is bigger than the table value, then we reject it. Okay. Whereas here it is not greater. So we cannot reject null hypothesis, and hence we will have to accept it. Okay, and here I have presented two different tables. You may get confused. Let me tell you, uh, here while defining these things, they have kind of given a hint to us that the larger quantity should be the numerator, and that should be the first coordinate of this f statistics, which means whatever comes first in the f statistic, that should be bigger or equal to the second one. So with a variety of tables available, uh, we are trying to find out 0.05 of 6 comma 4, isn't it? Okay, if you see here, they have specified it is v2. So here we'll have to look for this 4. Okay, and here 6. So it is 6.16. Now you may wonder, like, what is the difference between the previous one and this one? They are more or less the same, but here in this table we have values for all, like all the possible level of significance that we fix. Okay, and when you try to calculate f of 1 minus alpha, that is f of 0.95 of 4 comma 6, that is 4 6.95, is it it? So okay, anyway, that is not available here. So in this case, it is 1 upon f of 0.05 of 6 comma 4. From this we can very well calculate it. Okay, and coming here, uh, just a minute, I can show you it in a better way. If you see, this is what we were looking at. Okay, So in the top of the table we have values till 9. You may wonder why. See, it has values for more than that as well. Okay, I just showed you only the first page in the slide, and this is for 0.05, and this table continues the values for 0.01. So these two are the standard values that we use for f distribution. Okay, now hope we can move further. And we have another example which says that two lighting techniques are compared by measuring the intensity of light at selected locations in areas lighted by these two methods. 15 measurements in the first area had a standard deviation of 2.7 foot candles, and 21 measurements in the second area had a standard deviation of 4.2 foot candles. Can it be concluded that the lighting in the second area is less uniform? Use this level of significance. So from these things we were able to see that n1 is 15 and s1 sample standard deviation is 2.7, and n2 is 21 and s2 is 4.2. Okay. Usually the null hypothesis is sigma 1 square equals sigma 2 square. Okay. Can it be concluded that the lighting in the second area is less uniform? So the alternate hypothesis is sigma 1 square is less than sigma 2 square. Okay, at this level of significance. So f statistic is, since s2 is bigger quantity, so f statistic is s2 square upon s1 square, and we get this to be 2.42. Now that we need to read the value of 20 comma 14 at 0.01 level of significance. We just read the value from the table and we observe that. Okay, let us try to read that value. 20 comma 14, isn't it? So 20 is here and 14 is here, so it is 3.51. So this is the value that we have here. So f is not bigger than the table value, therefore we'll have to accept h naught. Okay, so even in this situation we can find the confidence interval. Okay, but how? The confidence interval is found for the ratio of variances. So uh, basically what we have is f of 1 minus alpha upon 2 n1 minus 1 comma n2 minus 1 less than uh, s1 square upon sigma 1 square divided by s2 square upon sigma 2 square. This is our f statistic, isn't it? F of alpha upon 2 times of n1 minus 1 comma n2 minus 1. This is what we have. We are trying to find out the confidence interval for this thing. So this shall be written as s1 square upon s2 square multiplied with sigma 2 square upon sigma 1 square. Okay, and these two quantities are there as it is. If you take this sample variance ratio to the other sides, you would get this confidence interval. Okay, in order to find f of 1 minus alpha upon 2 of this thing, you can very well make use of this formula to find it out. Okay, here we have an example. A sample data is given for two different samples, and we are asked to obtain the confidence interval. 98% is confidence interval for this thing. Okay, if you count your n1 is 8, n1 is 8, n2 is also 8, and using calculator you can very well calculate your s1 is 2.385 and s2 is 2.983. Therefore your f value, that is s2 square upon s1 square, which is 1.564. Okay, from the table we are able to read this value 7 comma 7, 7 comma 7 at the level of significance 0.01, that is 6.99, isn't it? So it is 6.99. So which implies f of 0.99 of 7 comma 7 is 1 upon 6.99, which comes out to be 0.1431. Therefore the confidence interval is, that is 0.1431 times of 1.564 less than sigma 2 square upon sigma 1 square less than 6.99 times of 1.564. You can very well simplify this and calculate what is the actual confidence interval. That's it. Thank you.